Hello, and welcome to this demo presentation on the topic of bipolar junction transistors. My name is Shadbin Sultana, and today I will be discussing the working principle of a bipolar junction transistor. First, let us look at the impact of this tiny electronic device. The bipolar junction transistor, or BJT, is one of the most significant inventions in the last century. Its importance highlighted by the fact that its inventors, Bardeen, Shockley, and Brittain, all went on to win the Nobel Prize in Physics for it. It is one of the most basic building blocks of today's modern electronics. We know that our daily life is built around this tiny device, and that the rise of the electronics industry is greater than ever. But to be able to join that race, we first need to ask the question, what really is a bipolar junction transistor? It's quite simple, really. The bipolar junction transistor, or BJT, is a three-terminal device with many uses, including amplification of weak signals into stronger ones and for switching purposes. As a result, it is an important part of both analog and digital electronics, and by extension, other related disciplines. Let us first look at the physical structure of a BJT. We may classify it as either an NPN structure or a PNP one, depending on the assembling of the N and P materials. The junctions in the device between the terminals have been specified as junction 1 and junction 2. Now, for this device to work, it is necessary that the width of the collector terminal is greatest and that of the base is lowest, while the doping concentration of emitter terminal must be highest, with that of the doping concentration of base being lowest. These are very important to remember as we look into the working principle. Now, one other thing before we dive into the main working part. To obtain a P or N-type material, we must first dope it. A P-type material thus will have a majority of holes and minority of electrons, and an N-type material will have a majority of electrons and minority of holes in it. Now, when we stick an N and P-type material together, due to these excess carriers I just mentioned, the electrons will recombine with the holes at the junction, but only up to a certain region. A barrier is formed at this junction due to the recombination of the electrons and holes, which will inhibit further recombination. This region, called the depletion region, I have shown by the green colored area. This makeup is actually a simple PN junction diode. Now, under no biasing, there is no more flow of any electrons or holes once the depletion region has formed. Except there is some flow, but that's due to the minority carriers from each side managing to pass through that barrier. However, if we connect the P side to positive terminal of a battery and N side to the negative terminal, we forward bias the diode as we make this depletion region smaller, allowing for majority carriers to flow. It is essentially a short circuit. If the battery terminals are reversed, we reverse bias the diode and it acts as an open circuit as the depletion region once more increases in width. So in the given NPN BJT, junction 1 has to be forward biased and junction 2 has to be reverse biased. These are very important. Now that we have these points down, let us look at a biased NPN BJT device. Now, as you can see here, junction 1 and junction 2. Junction 1 has been forward biased because the P side has been connected to the positive terminal and the N side has been connected to the negative terminal, and junction 2 has been reverse biased as the P side has been connected to the negative terminal and the N side has been connected to the positive terminal. Now, in this diagram below, the little white lines represent electrons and the little black dots represent holes. If you remember, I had mentioned earlier that the doping concentration of emitter terminal is highest, so you can see many of the white lines to represent that high concentration. I had also said that the width and doping concentration of base terminal is the lowest, which is why the middle layer is very thin and its doping concentration is also relatively low with the less number of black holes that I've put. So due to this, as a result, when we forward bias junction 1, we are allowing all the majority carriers in the N-type material, that is the electrons in the N-type material, to rush into the P-type material as shown by the red arrows. However, since the doping in this base layer is very low, as I previously mentioned, and since the width is very low, there is a very low amount of recombination between the injected electrons and the existing holes in this layer. Like the ratio of electrons and holes is very low, so the electrons will not have any holes to recombine with. So because of this physical constraint, the electrons will mostly pass into the collector layer instead of recombining in the base layer. Some, though, will still manage to recombine in the base layer and then flow as shown. Now, the red arrows that I have shown so far are the electron flow direction. So the conventional current directions of the terminals will therefore be indicated as the blue arrows. Now, one other thing I ought to clear is, why are the electrons even passing into the collector layer from the emitter layer directly? There should be a barrier at junction 2 which should stop it, right? But that's the thing. This junction, this second junction, junction 2, is reverse biased. So the injected electrons in the base terminal are the minority in this case. So since it is a p-type, the base layer is p-type, and we know that the minority carriers can move through the barrier into their preferred material based on the energy they have. So we can say that the electrons in the p-type are minority, so they will just move into the n-type where they can become the majority. So in this case, the sudden rush of the electrons will want to move into the n-type collector material. Now, we have two important relations. First one we obtain by applying KCL. Emitter current is leaving while the base and collector current are entering. So we can write IE equals the sum of IB plus IC, which is the first relation. Additionally, I had also mentioned that most of the electrons from the emitter pass into the collector, not all, the keyword being most. So that means if we consider a factor of alpha, which is less than 1, to show that the amount of successfully injected electrons from emitter to collector, we can say that IC is alpha times of IE. We could leave the relationship at that. However, there is another term, ICO, which is the reverse saturation current due to the minority carrier flow as the junction 2 is reverse biased. This reverse saturation current exists even under no bias conditions, so it must be added to the collector current equation. Now, I would like to end today's short demo on bipolar junction transistors by mentioning that the NPN transistor has the symbol as displayed. So for further analysis, we may redraw our circuits as so. For extended analysis and applications, we actually have a few different configurations depending on which terminal is connected to ground. So if the base is grounded, it is the common base configuration. If the emitter is grounded, then it is common emitter configuration. And if the collector is grounded, it is known as the common collector configuration. But no matter what the configuration, the operating principle of the transistor remains the same. Thank you.